You know how sometimes you ask a question, but the answer you get isn't a full out explanation of everything? Like this question: why does a plane fly fast? And this standard answer: because it has powerful engines. Yeah, so what does that really mean? It doesn't actually explain everything. Sure, an airplane has powerful engines, but what makes them powerful? What makes them spin? How does the plane get off of the ground thanks to them? The answer itself isn't wrong, it just doesn't account for everything. Precisely this problem exists in the standard Big Bang theory. There are two things that aren't accounted for by this theory that seem quite mysterious. They are the flatness and horizon problem. Why they're a problem, and how the notion of an inflationary universe patches up these problems for the Big Bang theory, will be made clear shortly. One thing the Big Bang Theory doesn't account for very well is why the density of the universe is so close to critical density, the average density of matter and energy that is needed to make space flat as opposed to curved. Our universe's energy density is made up of about 71.4% dark energy, about 24% cold dark matter, and approximately 4.6% of ordinary matter, that is to say atoms. And because it's so close to critical density, we believe it's almost completely flat in nature. This point leads me to the flatness problem, something the standard model of the Big Bang cannot explain or account for. The flatness problem is the interesting notion that the early universe had just the right amount of matter to make it flat. In other words, had the initial density of the universe been slightly much higher or lower than critical density, our universe wouldn't be flat and would be curved today instead. This means the density of the early universe was either exactly that of critical density or extremely close to it. The other problem is the horizon problem. This is the inability of the standard Big Bang theory to explain why the cosmic microwave background radiation is so incredibly uniform throughout our universe. Here's why this is a problem. The CMB we see on opposite sides of our sky once originated in regions of the universe that were much closer to one another. Even so, when the CMB originated at the era of decoupling at 400,000 years post the Big Bang, these regions were still millions of light years apart. That's an issue because, given the age of our universe, not even light could have traveled quickly enough to bridge such distances in order to exchange information between the two distant regions. In other words, had one region been hotter than the other, there shouldn't have been enough time for the hotter energy to flow to the cooler region to average out the temperature. Therefore, how is it that our universe is so uniform on a large scale everywhere you look, despite the fact that such regions apparently could have never interacted to equalize one another? I'll explain how in a second, but I do want to reiterate that the flatness and horizon problems do not negate or contradict the standard model of the Big Bang. It's only that this model doesn't explain these problems, why the universe is so uniform and why the universe formed very close to critical density. Therefore, something else must explain all of this, and that is where the inflationary universe comes in, a version of the Big Bang theory that accounts for the very rapid expansion of our early universe. Before I explain how inflation solves these problems, I need you to know something else. We know of four forces that govern our universe. They are gravity, the electromagnetic force, the strong force, and the weak force. Gravity you surely know of, as it has certainly helped you to fall down before. The electromagnetic force is the stuff that sticks magnets to metal, among other things. The strong force glues atomic nuclei together, and the weak force is involved in radioactive decay. From the very outset of the Big Bang, Astronomers believe that the electromagnetic force and weak force were combined into a single force called the electroweak force. The electroweak force was also combined with the strong force. Within the tiniest fractions of the first second following the Big Bang, astronomers believe that the strong force separated from the electroweak force. This released humongous amounts of energy that inflated the universe by 100 trillion, 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 trillion times or more. But prior to this inflation, the region of the universe from which we are receiving CMB radiation right now was extremely small, smaller than the nucleus of an atom. So small that despite the tiny time frames involved here, there was still enough time for energy to be transferred throughout this region in a uniform manner. This helps to solve the horizon problem. The flatness problem is solved by inflation as well. During inflation, the curvature of the universe neared flatness in the same way as inflating a balloon flattens out regions on its surface. Put another way, the universe might have actually been curved right as it was created. However, expanding it out to such epic proportions during the inflationary epoch caused its curvature to flatten out like a balloon when it is inflated. One thing the Big Bang Theory doesn't account for very well is why our universe's density is so close to critical density, the average density of matter and energy that is needed to make space flat as opposed to curved. This leads to the so-called flatness problem, the interesting notion that the early universe had just the right amount of matter to make it flat. Furthermore, the standard Big Bang model has another problem called the horizon problem. This is the inability of the standard Big Bang theory to explain why the cosmic microwave background radiation is so incredibly uniform throughout our universe. The inflationary universe, a version of the Big Bang theory that accounts for the very rapid expansion of our early universe, helps to solve these problems for us in a different way. During the smallest fraction of the first second after the Big Bang, the strong force separated from the weak force, and this caused the universe to inflate or expand by a huge factor. Before this, the universe was small enough to allow for uniform exchange of energy, which accounts for its large-scale uniformity today. Furthermore, the inflation of the early universe flattened it out, like the curvature of a balloon flattens out on its surface when it's inflated, thus helping to solve the flatness problem.